And last time, if you remember, we looked at a worked example from Oppenheim and Schaefer, where we said we have a sinusoid cosine 4000 pi t. I want to sample it omega s equal to 1200 pi, and I will look at all the where the copies of the signal are coming. Okay. Now, we want to look at the same problem, but we will look at it in a slightly different way with a different sampling rate. Okay, so let us quickly do that, because it's going to be very instructive for us to do that. So this is part B of the same example. It's a continuation of the same example. Okay, we have a continuous time signal xc of t equal to cosine 4000 pi t. Okay, so we know that the maximum frequency in this case is equal to 2000 hertz. 2000 hertz. Okay, so the Nyquist rate will be equal to 4000 will be equal to 4000 sorry twice the maximum rate will be the highest frequency component is 4000 pi, and the Nyquist sampling rate will be 8000 pi. Okay, this is the Nyquist rate. This is the Nyquist rate. Okay. Now, last time, if you remember, we used a sampling frequency equal to 12,000 pi. Okay, this was in part A. And so this one was oversampled system, and we showed how we can how the different copies of the spectrum come out to be, and how we can look at the signal. And if you look at the spectrum of the signal that we are looking at, last time we wrote it down. So basically there are two impulses, one at pi over Ts and the other one at minus pi over Ts, at 4000 pi and minus 4000 pi, the height of the, so basically the xc of j omega, okay, this is at 4000 pi and minus 4000 pi. 4000 pi minus 4000 pi, and the height is pi over Ts. Okay, and we had a good way to create all of the copies. We said the let's just copy this. Then we don't have to rewrite the whole thing, except that we will have to modify it for the following condition. Okay, so we are going to use a sampling frequency. Okay, pay close attention. We are going to use a sampling frequency omega s. Okay, what should be the omega s? It should be 8000 pi, right? But I am going to use 3000 pi. Okay, I am going to use 3000 pi. So which means that I am going to run into aliasing. And how is aliasing going to manifest itself in this particular case? So the k equal to 0, no problem, it will occur at the same location. Okay. Now k equal to 1, the first copy of the signal, where is that going to come? It's going to be the center frequency plus the frequency of the sinusoid. This is going to come at 7000 pi. 7000 pi, and the corresponding signal is 3000 pi minus 4000 pi. So this delta function is going to come at minus 1000 pi. Okay, let's do k equal to 2. K equal to 2 will be centered around 6000 pi plus 4000. It comes out to be 10,000 pi. 10,000 pi. This one comes out to be 6000 minus 4000. So basically this will be 2000 pi. 2000 pi. Okay. Now k equal to minus 1. Just like if you look at that, it is at minus 3000. So minus 3000 plus 4000 pi will be 1000 pi. Okay, just do exactly what we did last time, just and then we will do the interpretation. 1000 pi, this will be at minus 7000 pi, and k equal to minus 2. Minus 2 will be at minus 2000 pi, and this will be at minus 10,000 pi. Okay. So, basically what you will get is a spectrum that looks like this, but now has got the Dirac delta functions at different locations. So, let us quickly draw what this new spectrum looks like. Okay, I will have to draw it in a careful manner. I will have to make sure I get all the different things that I have. So, if this is 4000 pi minus 4000 pi, okay, let me make it green so that it will be consistent with the color combination that I have done. The first copy of the signal, okay, it is going to be at minus 1000 pi and at 7000 pi. Okay, and let me make this a little straight. Minus 1000 pi and 7000 pi. And then the next copy of the signal is at 2000 pi, is at 2000 pi and 10,000 pi. So, this is 4000, 7000, this is 10,000. Okay. And similarly on the other side, I am going to see 1000 pi. Okay, there is going to be a signal at 1000 pi and a signal at minus 7000 pi. These are this is corresponding to k equal to minus 1, and then another signal at minus 2000. This is minus 1000, so this is minus 2000 and then minus 10,000. Okay, let me just write down the frequency so that there will be something there. So, this is 7000. Let me just write 7. Okay, so this corresponds to 7 multiplied by 1000 pi. Okay, whatever is the multiplied by 1000 pi. So, this is 7000 pi and this is minus 1. Okay, this is minus 4 and 4. Blue is 2 and 10, and the purple is 1 and minus 7, and the dark blue is minus 2 and minus 10. Okay. Now, height of all these, all of them are at pi over Ts. Okay, no issues. Now, when you want to do the reconstruction, remember what was the definition of the reconstruction filter? If this is your omega s, the reconstruction filter will be an ideal low pass filter with a height equal to Ts, right, and it will go from minus omega s by 2 to omega s by 2. Okay. So, what is that in actual frequencies? This is going to go from minus 1500 pi to 1500 pi. That is going to be the reconstruction filter. Okay. Now, apply the reconstruction filter and let us see which delta functions are actually going to get retained. Okay, that is 1500 pi to minus 1500 pi. And so, what you will get when you do the reconstructed signal xr prime of t, okay, what are you going to get? You are going to get cosine 1000 pi t, because these frequencies, what delta functions were retained was plus 1000 pi and minus 1000 pi. Okay. So, now this is going to be a different reconstructed signal. Your original signal was cosine 4000 pi, but in the process you ended up, because of the you did not satisfy Nyquist criterion, you ended up introducing aliasing, and the alias signal, when we reconstructed, it gave us a completely different signal in terms of the reconstruction. Okay, very important important aspect. Okay, now I want to also take a small portion of the page to discuss what happens in the process of sampling the signal. Okay, I have x of n, which is continuous time signal xc of t, which is sampled at t equal to nts, correct? So, this is cosine 4000 pi n ts, where ts is equal to 1 over 6000. Okay, that is what we have. That is how you get omega is equal to 12,000 pi. This implies Ts is equal to 1 over 6000, because omega s is equal to 2 pi over Ts. Okay. So, now substitute, what do you get? Cosine 4000 pi n divided by 6000. This is the same as cosine 2 pi by 3 times n. This is the discrete time signal that we will get. This is the discrete time signal that we will get. Okay. Now, what I want you to do is come to this signal and say that, okay, if I have cosine 1000 pi t, this is my continuous time signal, and I am going to sample this at t equal to nts, where ts is equal to, or what is my sampling frequency, 3000, this is going to be 1 over 1500. Okay, that is my that is my ts. So, if I convert this to a discrete time signal, then what will I get? I will get cosine 1000 pi n, ts is 1 over 1500. If you see, you get cosine 2 pi by 3 n. Now, what is the important thing that we need to take away from here? Remember that the discrete time frequencies are periodic. Okay. When you go from discrete time to continuous time, the frequency that you will get in the continuous time depends on your sampling rate. Now, if you change the sampling rate, for which you have done in this particular example, okay, you change the sampling rate, you got a different, the same discrete time signal, cosine 2 pi by 3 n gives you cosine 1000 pi t in one case, gives you 4000 pi t in another case. And because the importance of the sampling period is extremely important. So, let us write down a few things that are important for you to keep in mind. Okay. Below Nyquist rate, so observation number 1, below Nyquist rate we will get aliasing. Okay. If you have aliasing, with aliasing we will not get back the original signal when reconstructed, will not get the original signal via reconstruction. Okay, a very important thing to remember, a signal via reconstruction. Okay, and in the reconstruction process, the sampling period plays a very important role. Reconstruction process, Ts plays a very important role, because this is what determines what frequencies will appear in the continuous time signal. Important role. Okay. So, we also saw that the same digital signal, same discrete time signal, discrete time signal which was cosine x of n equal to x of n equal to cosine 2 pi by 3 n gave us two reconstructed signals. It gave us cosine 4000 pi t with Ts equal to 1 over 6000, which satisfies Nyquist rate. It also gave us cosine 1000 pi t with Ts equal to 1 divided by 1500. Okay, so the same discrete time signal can produce multiple various continuous time signals. Again, we want to keep that in mind and keep all of these concepts in a way that you can use it to quickly visualize what is happening in the process of sampling. Okay, if there are any questions about this, please do post it on the group and Mr. Tony will address it when we have the live interaction session.